Hey everyone, welcome back to the channel. So today we will be discussing another problem from our DP section of SD sheet. Let me just check if I'm live, then I will show you the question. Yes, we are. Okay, so we will be discussing coin change problem. I'm pretty sure you must have already seen this problem a lot of times, and it's an important and a nice question. So let's understand. There are lots of variations that are formed out of this question. So you are given an integer and sum. Okay, so you're given a coins array which you can consider having denominations which you have in terms of coins. Okay, so these are some denominations that you have, and this is the total sum that you have to pay with these denominations. Okay, so what you have to tell, in how many combinations, how many such combinations are possible in which you can pay a total sum of 4. So let me take this example and help you understand. So for example, your total sum is 4, right? And the coins that you are given is coins array are containing denominations 1, 2 and 3, right? Now see, you have to pay a sum of rupees 4 and you have these 3 coins, and there is infinite supply of each coin. That means there is no limit to how many times you can take any coin of any particular denomination, right? So let's understand how many such possibilities are there. If I take this example, I'll just start with the recursion tree, as you know that we always start with it, so that you understand that how many possibilities we are going to get for this case, which needs some optimization. That's where we lead ourselves to the DP's approach. Okay, so I have a sum of 4, right? And I have 3 varieties of coins here. If I choose to take, for each case I have 3 possibilities. If I choose to take coin of rupees 1, if I choose to take coin of rupees 2, if I take 3. If I take a coin of 1, then I will be left with sum of 3, right? Let me just complete one branch, then we will move to other. Now tell me, you will say I have already used coin of denomination 1. Should I go to directly 2 or 3? No, I can use any coin as many times I want, unless I am paying my sum and it becomes to 0. I want to complete this sum that I am paying. So right now my sum is 3. Let's pay it using 1 rupee coin. So I will explore all the possibilities. Then we will see that how many unique combinations we are getting. So now if I use coin 1 again, which I am allowed to, the sum I will be left with is 2, right? From here I come here. Let me try out. I will fill up these possibilities. First I'll just try completing them. I'll go from bottom. Okay, so I used coin 1 for this. When my, okay, let's do it from here only, from top. Now when I was at 3, I already used a 1 rupee coin. Now the other option that I have is to use other 2 coins, which are coin 2 and 3, right? So if I use a 2 rupee coin, okay, if I use a 2 rupee coin, what will be my sum left now? I started with 4, I used 1 rupee coin. Now with ones I have already explored, I am trying out the other possibilities. For 3, again, for every node has 3 options. Those 3 options are the denomination that I have in my coins array, right? So now when I use a 2 rupee coin, the sum that I will be left with is 3 minus 2, that is 1, right? Now for 1, again I will have how many options? I'll have 3 options for 1 again. That is a different thing, whether I'm able to make use of that denomination or not, but the options will be 3 for every node, right? Now if I choose to take 1, you will see that there will be a lot of branches that are still unexplored, and I'm not going to complete this tree, but this will be enough for you to understand that how many options will be having for each node, right? And there will be so many overlapping cases as well, because you will see that in the subsequent branch I will have so many nodes that are having the same sum, and I am repeating my case for lot of such nodes. That is where the repetition of calculation is happening, right? This is the reason this recursion takes higher time complexity. Okay, so when I use a denomination 1, my sum becomes 0. So this is also one combination. Let me write this combination. So this combination is, I used 1, 2 and 1. So even if you make do total of these denominations, I used 1 twice and denomination 2 only once. So total sum is 4. As long as I'm satisfying the total sum, I am going to count that particular combination if it's unique or I haven't already calculated it. Next up, what I have, when I was at this position, I used 1 rupee denomination and I calculated my combination for that. Can I use 2 rupee coin? No. Why? Because my sum is not enough to be paid by a 2 rupee coin. You see that? I have a sum of 1. If I use a 2 rupee coin, I'll be left with -1. What is -1? There is nothing like -1 that I have to pay someone. That is debt. Means we're not going to consider such cases. So as long as my sum is 0, that means I have found my combination. If it goes beyond 0, that means I am not able to satisfy my sum what I started with the combination that I am going through in the branch. So if I am trying to take a combination which is 1, 2 and 2, so you will clearly see this is not able to satisfy me a sum of 4 that I wanted to, right? This is the reason this is not going to be a valid combination. So no answer from here. You just have to calculate how many such combinations are possible. So from here I'll move towards the conclusion that whenever I get a sum of 0, that is where I will get one combination, one of this. So whenever I get a sum of 0, you will know that you have found an answer which is going to be 1, at least for that particular branch, and this 1 is the number of combination that you have found. So basically when you'll see that this branch will give you a sum of 1, answer 1, then this branch will also give you an answer 1. You will add up all the combinations that you have found from the case when your sum becomes 0. The moment, so basically such combinations you are returning, that will be added up finally to the case which has made these calls. Okay, so for this, how many we are getting? We are getting total 4 such possibilities. Now think it like what we have been doing from in the previous lectures as well. Now think of it that making use of the answers that I am calculating for the smaller sub problem. How can I solve this problem in a reduced time complexity? So you can see, for at least for this, if the length of coins array is n, right? So how many possibilities I'm going to have? Sum is m, sum let's say is n, coins is m, right? So you will see that n to the power m, I don't know how much it will become, not sure what calculation it will give me, but you know that it's going to be exponential. Why? We can calculate it for sure. 3 cases for this. Then if I talk about this particular example, then how many? 1 2 3 for this. So how the number of nodes you are going to have, you will be having these 3 as many times. So basically m to the power n, something like that. So if I take, now let's come down to our DP approach. I just want to do what? Have a look. So my coins array is 1 2 3 and my sum that I want to satisfy is 4, right? So see, if I take my sum, okay, and I see that for every sum I am using each coin and I am trying to see that with each coin how many combinations I am. If my sum is 0, if my sum is 1, 2, what is the total sum? 4. So I'll take a DP whose length will be equal to sum plus 1, right? My DP's length will be sum plus 1. Now one by one I will consider each coin and I'll see that how many combinations I can create using that coin for these sum that I have taken in my DP array. Okay, so if I use a coin for sum 0, your answer will always be 1. Your combination, that means the number of combinations for sum 0 will be 1. Why? Relate it with our base case. Whenever we are getting sum 0 going from top to bottom, right, in that approach, whenever my sum is 0, that means I have got one combination, right? That's when I am leading towards 0, right? So for that purpose, for that calculation purpose, we are going to make this answer for 0 as 1, thinking that whenever my sum is 0, there is one possibility, that is you are not taking any coin. You can consider it in that way also. So for sum 0, one combination is always possible. So we have pre-filled this value with 1. Now let's start calculating it for this. The coin, this is the coins array, right? Right now my coin is 1 and I will calculate that with one coin how many combinations are possible for each of the sum, right? I'll calculate for smaller ones, and finally the answer here will tell me that number of combinations possible using sum 1. I'll repeat the same process for the remaining coins in my coins array, and finally the answer here will keep adding to each index. Every coin will add up their combinations to the existing ones, and finally the answer that I will have at this index will be my total number of combinations, right? So let's see. If I have a coin of rupee 1, I will check, is my sum that I am currently present at, this sum, is it even greater than the value that I am denomination that I am taking? So if the current sum is greater than my coin size, definitely I can use that coin. So if I can use that coin, what is the remaining sum? Sum will become equal to this current sum minus coin size, right? And that will be given to you as 0. So you have to actually check what is present in this new sum. You can write n sum. So dp of n sum, okay, this should ideally give you the number of combinations that are present for that particular n sum, and I will just simply add this answer to my current dp of I plus equal to dp of that current value and the number of combination I am getting by using this coin. So if I am taking this coin 1, so the sum I will be left with 0. So how many combinations were possible for 0? It was 1. So I'll get at least one combination, right? That means by using this one coin I can get a sum of 0. That means I'm able to pay this sum that I'm trying to calculate by making use of this coin. Okay, let's move ahead. I will first check all the number of combinations with this coin, then this coin, and that coin. Now I'll check, can I pay a sum of 2 with 1 rupee coin? Yes. So now the sum that I'll be left with is 1. So 1 rupee, in how many combinations can I get a sum of rupees 1? That will be given to me. This is your dp array. That will be given to me by dp of 1. So dp of 1 is 1. So current value is 0. You will add this answer to the current answer. That means you can get 2 as a sum by making use of 1, and that combination will be 1 1 only. That is why we are getting total combination here as 1. Same thing do for 3. If I make use of 1 for 3 as my sum, what is the sum I'll be left with? 2. Ask your dp of 2. In how many ways were you able to get paid? Okay, were you being paid? So only in one combination. So that combination I'll add here, which tells me that I am able to pay a sum of 3 by using 1 rupee coin. What are those combinations? That's not what we are going to solve here. We are not going to give an array list of those combinations. We are just giving the count of such combinations. Same goes for 4. If I make use of 1 rupee coin, I'll simply check that 4 minus 1, 3. dp of 3 tell me in how many ways were you being formed. It tells 1. So I'll just add that answer to myself. Repeat the same process for 2. Start from this index, first index. So first of all, you'll see the sum that you are satisfying here itself is less than the coin that you are taking, coin size. So in that case, there is no point of calculating the sum. Go ahead. Okay, so this will not be satisfied. Now I am at this index, right? So I can make use of 2 rupee coin. So 2 minus 2, 0. Ask dp of 0, what was the number of combinations for you? It says 1. So add that combination to my current combination. It will become 2, right? Okay, move to the next index. Here I am. Can I make a sum of 3 using coin 2? We'll see. If I make use a coin 2, I'll be left with sum of 1. Ask dp of 1. Now see what it is representing. Every block is representing in how many ways were you, if 1 is my sum, in how many ways can I pay a sum of 1 by using whatever coins I have so far. So no matter what are those combinations, but it will tell me the number of combinations. Simple thing that when I am paying it with the rupee 2, so I will be left with rupee 1. So that rupee 1 was being paid in only one combination. So add that to yourself. So this will become 2. And actually what are those combinations, since so far we have used only coins 1 and 2. So 3 shows that you are being formed in 2 combinations. And actually what those combinations are, I'll show you. 1 1 1 and other combination will be 2 and 1. Okay. we are not considering the permutations, in case you think this is also one combination. So we are not considering the permutations, only combinations, right? So two combinations possible. Now check for same. If I am paying it with a rupee 2, what is the sum? I'll be left with 2. So add that combination, number of combinations to yourself, which is 2 plus 1, 3. Okay, so total 3 combinations so far. Let's take 3 finally. Now for 3, you know that as long as the sum is less than the coin's I value, there will be nothing new, no new combination that you can create. So I'll directly start from this index. Why? Because this is the this is the sum that I can, minimum sum that I can pay with using 3 denomination is 3. So if I pay with 3, I'll be left with sum 0. Ask DP of 0, number of combinations for you 1. So add this value to your current value, that will become 3. So total combinations for 3 is 3. Now check for 4. So if I pay 4 sum with rupee 3, so I'll be left with 1 as my sum. Ask DP of 1, in how many ways were you formed? Combination says 1. Add that to your current answer. So this will become finally 3 plus 1, 4. So what is the answer you're getting for sum 4? So now finally all the iterations for coins array is done, and this DP of 4 tells you that this was the sum that was needed to be paid using these coins, and total combinations are 4, right? So that is all about it. I'll just check if we are live. Still, you guys can see me. Yes, we are. Okay, so that's all that we have done. Let's have a look at our code now. So you can see that the question asks us to return the answer in long type. Number of combinations can go up to long data type. So we have created this DP array of type long. You know why I have taken of length sum plus 1. If sum is 4, the length will be 5. If sum is 10, your length will be 11. So all in all, if you see that this is taking you big of m cross n time complexity, or you can say sum multiplied by the length of this coins array is the time complexity, right? At least we reduced it from exponential to this om into n, right? Okay, so in this DP, I am iterating over my coins array, and for each sum starting from sum 1, because sum 0 will have combination 1 which I have already pre-filled. So I will check for each coin, I will explore all the possibilities of my sum, fill my answer. That answer is, see, coin value is coins I will check if j, you can do it in any way. If that current, this represents that the coin that you have selected, that's this coin value, right? If, what is this coin value? For example, if you are choosing 1 and the sum that you are trying to pay, this j is nothing but the current sum that you are at. Only if it is greater than or equal to your coin value, you evaluate the answer. You know that. This is nothing, very simple for loop. Just you need to understand what we discussed just so far, and this is very simple. Now, if that condition holds true, only then you will be calculating the number of combinations, right? So that current DP of that particular j is that current sum, is equal to that whatever is the current answer plus the number of combinations you got by using that particular coin. So what is the remaining sum? Current sum minus the coin that you used. So that the remaining sum in DP will have your combinations for that particular sum. You will add it to yourself. And finally, DP of sum, because the length of your DP array is sum plus 1. So the last index will be sum index. So you return that value, and that is all about it, right? DP codes are always simple, but you see what goes behind it. The logic needs to be very clear, right? So that is all for today, everyone. And if you have any doubts, you can ask me. Otherwise, we will wrap it up. Fine? Okay, guys, then let's wrap it up and see you all in the next lecture. Bye.